In this video, we are going to examine 5 main factors that affect the solubility and rate of dissolving of a solute. The first factor that we are going to look at is temperature. So an increase in temperature causes the spaces between particles to increase, and that means that there is more space for particles of solutes to dissolve. In terms of solids dissolving in liquids, as you increase temperature, the solubility increases. And that's because when a solid dissolves in a liquid, energy is needed to break the strong bonds between particles in the solid. At higher temperatures, more energy is present. That means that solubility of most solids will increase with temperature. But then if you take a look at gases dissolving in liquids, as temperature increases, the solubility generally decreases. And that's because gas particles move quickly and have a great deal of kinetic energy. When a gas dissolves in a liquid, it loses some of this energy. At higher temperatures, the dissolved gas gains energy again. So as a result, the gas comes out of solution and is less soluble. The second factor that affects solubility is pressure. As pressure increases, the solubility generally increases for gases that are dissolving in a liquid, but generally an increase in pressure has no effect on the solubility of solids. So let's take a look at an example. For example, in gases, when you open a carbonated drink like the Coke shown in this slide, you can observe the effects of pressure on solubility. So inside this soft drink can, the pressure of the carbon dioxide gas is very high. When you open the can, you hear the sound of the escaping gas as the pressure is reduced. So what's happening here is carbon dioxide gas is escaping quickly from the can since the pressure of the carbon dioxide in the atmosphere is much lower. The solubility then of the carbon dioxide in the liquid soft drink decreases greatly. And so all of the gas will come out of solution and escape. The third factor that affects solubility is molecule size. Generally, as molecules get bigger, the solubility decreases. So for example, methanol, which is a really small alcohol, has the structure CH3OH, is quite soluble in solution. But if you take something that's much longer now, that has a much longer carbon chain, like, for example, pentanol, so 1, 2, 3, 4, 5, it's a much, much bigger molecule now, and so far less soluble in water. The fourth factor that affects solubility is the surface area. So as surface area increases, the solubility will also increase. So for example, if you had just one square block that you were trying to dissolve versus lots of tiny little pellets, the one with the tiny pellets is going to dissolve faster because it has a greater surface area than the solid that is just one simple block. So this has low surface area. The final factor is that will affect solubility is the type of solvent or solute particles. Generally, polar solutes are going to dissolve in polar solvents, but polar solutes do not dissolve in nonpolar solvents. The same is true for nonpolar solutes, so we get vice versa, where nonpolar solutes will dissolve in nonpolar solvents, but they do not dissolve in polar solvents. So why is this the case? In order for a substance to dissolve in another substance, there must be an attraction between the molecules of the solute and the solvent. Ionic and polar solutes will dissolve in polar solvents because the particles of both substances are charged, whether that is full charges, so full negative and positive charges, or whether it's partial positive and negative charges. So remember from our first unit that polar means slight regions of charge. So the change in electronegativity of polar molecules is somewhere between 1.6 and 0.5, and for ionic compounds, it's greater than 1.7. Nonpolar solutes will only dissolve in nonpolar solvents. So although the particles have no dipoles or charges, they share the common characteristic of being nonpolar and therefore will dissolve in one another. So we are defining nonpolar molecules as those with a change in electronegativity of less than 0.4. This relationship then can be summarized in the expression like dissolves like. So polar is going to dissolve polar, and nonpolar is going to dissolve nonpolar.